Institute of Engineering and Technology.
Good morning, students. Today we are going to start a totally new category of higher order differential equation known as Legendre's equation. This is a very particular type of higher order differential equation. Till date we have seen higher order differential equation with constant coefficients. This is the extension of that towards variable coefficients. We have seen how to solve higher order differential equations using complementary function and particular interval. There is a detailed video series about a constant coefficient higher order differential equation. This is just extension in the same direction where we are dealing with the coefficients which are depending on x, and they are also in a particular manner. Later on, we will see its special case known as Cauchy-Euler equation. Okay, so this video is all about variable coefficients into higher order differential equation. So let us start this chapter. So the definition of this Legendre's equation is a0 ax plus b raised to n y raised to n. This indicates nth order derivative of y with respect to x. This means that y is dependent variable on free variable x. And coefficient is a0 times ax plus b raised to n. It cannot be any random coefficient. It must be ax plus b raised to n. That is a specific role of this power and this order of derivative. They must be equal. Second term is a1 ax plus b raised to n minus 1. Order of derivative for y is also n minus 1, and up to so on is a n y of x equal to r x. All a0, a1, a2 up to so on an are arbitrary constants. Rx is a random non-zero function of variable x. So if we have this situation, means if we have this particular type of equation in example to solve, where the coefficient is variable, particularly ax plus b, and order is equal to the power of that term ax plus b, and then only this method is useful. So the first step in this method is to take assumption of ax plus b equal to e raised to x. Once you take ax plus b equal to e raised to z, it gives you log of ax plus b equal to z. Now this will change ax plus b into y raised to derivative n into this linear term. It will give you a raised to n dz into dz minus 1, dz minus 2, dz plus n minus 1. Okay, so actually there are n d terms, and over here we have nth order derivative. See, up to now we have seen the differential operator d. By default it was representing derivative with respect to d. But as over here we changed our free variable from x to z, my differential operator will also change from d to d subscript z. D subscript z indicates derivative with respect to z. So the whole role of assumption is to convert this variable coefficient into constant coefficient. Once we convert our equation into the constant coefficient, again we can go back to our regular three methods: special functions, method of variation of parameter, or method of undetermined coefficients. So basically this Legendre's equation will give you one additional step in the beginning and one additional step at last. To convert z from x from z, solve equation in z using our regular technique, and in last step you convert again z into x. So this is the main assumption which will help you to identify. This assumption will help you to identify the regular constant coefficient higher order differential equation. And then, as I told you, you can use any of these three methods to find the answer and then replace z with x. So this is the algorithm. Replace x to z, convert all variable coefficients into constant coefficients, use one of our regular method, and then finally once you obtain the general solution, convert z into x. Let us go through one example. Suppose this is the equation x plus 1 whole square y double dash plus x plus 1 y dash plus y equal to x plus 1. How to solve this? You cannot apply any of your regular methods in this case as the constant multiples are not available. There are variable coefficients x plus 1. Now see, they are repeated x plus 1, x plus 1, and also the power is equal to the order of differential equation. So that means this is a very particular case of variable coefficients, which is known as Legendre's equation. Okay, so whatsoever be the multiple over here, take that equal to e raised to z. So here a equal to 1 and b equal to 1. I am comparing this with this ax plus b equal to e raised to z. So first step a1 b1. Therefore z is log of x plus 1, taking natural log both sides. And that means now I want to convert my all possible derivatives. As of in this case, it was given by this equation. I am following the same rule to find first and second order derivatives. So x plus 1 whole square y double dash is 1 whole square. This 1 is nothing but a. Okay, value of a. And that we have seen over here, that value of a is used in multiplication. Okay, so x plus 1 whole square y double dash is 1 square. Two components of d will be there, dz minus 1 times y. X plus 1 y dash is 1 raised to 1 dz of y. This is how you can find all possible differential operators in terms of dz. Now look, what is the difference? Over here there is a variable coefficient, and over here there is a constant coefficient. Okay, so that means now we converted all our variable coefficients into constant form. So my equation will be like this: dz into dz minus 1y, that is value of x plus 1 whole square y double dash, and value of x plus 1 y dash is dz of y, value of y as it is, and on the right hand side x plus 1 is nothing but e raised to z. And that means now I converted my whole equation from free variable x to free variable z. Don't forget to consider dz, otherwise you will be confused that what is the variable of derivative. So now I am simplifying this. It gives me dz whole square minus dzy plus y equals to e raised to z. Simplifying this will give me d square z y plus y equal to e raised to z. Taking y outside, it gives me d square z plus 1 y equal to e raised to z. Then the rules are same. Here I want to find complementary function, so auxiliary equation is f of dz equal to 0, which gives me d square plus 1 equal to 0, so roots are 0 plus or minus 5. Remember here the free variable is z, not x. So complementary function will be yc of z. So it is c1 cos z plus c2 sin z. In place of x, simply I am taking variable z. Rest of the methods are same. Now, for particular integral, we have 1 upon f of dz rz. Now here we have e raised to z, so we can treat this as a direct method case 1. Replacing z with 1, it gives me 1 upon 1 square plus 1 e raised to z. So answer is 1 by 2 e raised to z. And therefore pi is e raised to z by 2. So general solution can be obtained by combining ycz and ypz. It gives me c1 cos z plus c2 sin z plus e raised to z by 2. Now coming to the last step, that is converting back z into x. We know that z is log of x plus 1 and e raised to z is x plus 1. And so value of y of x will be c1 cos z. Z is log of x plus 1, so it is cos of log of x plus 1 plus c2 sin z, it is sine of log of x plus 1 plus x plus 1 by 2. This is how you can find solution using our regular technique with help of that assumption, which will convert your variable coefficient into constant coefficient. Now, as I told you, there is a very special case in Legendre's equation. If A equal to 1 and B equal to 0 in Legendre's equation, then it is known as Cauchy-Euler equation. Let me come back to this part. If A is 1 and B is 0, that means there is only term over here which is x. So the general form will look something like this. If we have x square y double dash minus xy dash plus y equal to x plus 1, suppose this is the question, then you can treat this by Legendre's equation also. There is no difference in between Cauchy-Euler and Legendre's equation. It is simply a special case of Legendre's equation. So here I am taking this bracket equal to e raised to z, a equal to 1, b 0. Z is log x. X square y double dash. I am finding all possible values of this variable coefficient in form of constant coefficients. So it is x square y double dash equal to dz minus 1. Suppose you have y triple dash, then it will be dz minus 1, dz minus 2. And so on, you can extend it up to nth order derivative. X plus 1 y dash is dz of y. Now taking this y double dash x square and xy dash, in over here it is x, by mistake it is written x plus 1, it is xy dash. So it will take from x square y plus xy dash plus y equal to x plus 1. Now this will be equal to dz minus 1y plus dz of y plus y equal to e raised to z plus 1. Simplifying this will give me d square z minus 1y equal to e raised to z plus 1. So for complementary function I am taking auxiliary equation d square z minus 1 as 0. So we have two roots, 1 and minus 1. So considering case of non-repeated real roots, my yc will be c1 e raised to z plus c2 e raised to minus 1. Okay, now taking 1 upon d square minus 1 on e raised to z plus 1. Now taking separately this term on e raised to z and on 1, and we know that the constant term can be rewritten as e raised to 0z. So I will replace d with 1 in this first part and I will replace d with 0 in the second part. If I replace d with 1, my denominator will be 0. So I need to multiply outside by parameter. Now remember here parameter is not x, it is z. So I am multiplying it by z, taking derivative in denominator. So it is 2 dz e raised to z plus 1 upon, replacing this with 0 will give me minus 1. And then this part will be 1. So it is minus 1. And here I am taking z into 1 by 2 and 1 upon dz indicates integration with respect to z. So it is e raised to z dz. So finally my answer is z e raised to z by 2 minus 1. Combining it with yc and then converting z into x by z equal to L log x, e raised to z equal to x will give me final answer. C1x plus C2x inverse plus log x into x by 2 minus 1. These are some examples for your practice which will help you to consider Legendre's equation and Cauchy-Euler equation. To recall the whole chapter, I will suggest you to go through these 5 examples. It will make clear that how good you are at direct methods, method of undetermined coefficients, and method of variation of parameters. Thank you.
LJ Institute of Engineering and Technology.